Hello everyone, I am Shoumi Das from IIT Kharagpur presenting our paper TMCOSS Thresholded Multi-Criteria Online Subset Selection for Data Efficient Autonomous Driving. This is a joint work between IIT Kharagpur and Hewlett-Packard Labs. Large fleets of autonomous vehicles are released every day for collecting data using different sensors. This leads to a collection of a huge amount of data. Here is an example of a scenario of a car driving on two types of roads. The first row of images shows some frames from the straight section. The bottom rows depict the frames during a right turn. Straight road frames are mostly having similar views, thus turning out to be redundant. However, the images during the turn are having changing views aided with differences in steering angles. These frames will be necessary for the training models to decide its move at junctures. Our aim is to study the problem of data-efficient autonomous driving systems. As we have seen earlier, straight road frames are mostly redundant, while the turn frames help the car to move at junctures. We show an example of episode completion here, trained using uniformly skipped subset. It fails to complete more than half of the episodes. Hence, we propose a multi-criteria online subset selection framework for selecting informative frames. We present a high-level picture of the selection framework. The car provides video feeds. There are two blocks. One is the multi-criteria OSS framework. The other is the stored data, where some existing data is present in the reduced data block. And the required model parameters are also available. However, the training using the data is happening on the cloud, after which the parameters are being shifted back to the stored area. The existing data, the incoming frames, and the model parameters go as inputs to the selection framework, which returns some selected frames that gets added to the existing data. This entire selection operation can happen on an edge device. This is the overall block diagram of how online subset selection works. We have an existing set, an incoming set arriving at an iteration t, and this module of the selection algorithm that takes both the sets as input and finds representatives. If any representative is found from the incoming set, it gets added to the existing set for the next iteration. The high-level idea of our work is, given a compression ratio, we want to find the frames which have the least dissimilarity and highest task-specific loss. The least dissimilarity ensures that the ones which get chosen as cluster heads improve diversity. The high task-specific loss ensures that frames failing to predict some situations get chosen so that post-training on such selected frames, the model improves on those tasks. Thus, we design a framework that takes care of both these pairwise and pointwise criteria. We name our method TMCOSS, a Thresholded Multi-Criteria OSS. We use facility location objective function involving multiple criteria. Here G is the objective function that has two optimization variables, ZO and ZN, which are denoting whether an incoming element is represented by an instance from the existing set O or incoming set N. There are three constraints. The first one, ensuring each incoming instance has one representative only. The second being the domain of the optimization variables, and the third being the compression ratio or the cardinality constraint, where we plug in the fraction of instances to be selected. The objective function G gets expanded where we see that the first part checks on the pairwise metric, while the second part looks at the pointwise metric. Both these metrics are weighed by a factor of rho. The last part is defining the variable associated with the pointwise metric, which defines the representative power of each element, thresholded by epsilon. Basically, any element having its L1 norm of representative value higher than the threshold value can be considered a potential representative. This thresholded S variable is a key innovation in this paper. Coming to the justification for thresholding, this is the theorem that mentions the conditions for an instance from an incoming set to become a representative. They state that an incoming instance J can only be a representative for an incoming element I if it has the least function value Qij compared to any other element. This Qij is a function used in our earlier work where it's defined as a weighed function of pairwise and pointwise matrix. This is its objective function where we can see that there is no direct relation with the compression ratio. Also, when we put all the weight on the pointwise metric, that is rho equal to 0, we can see that the dependency on I does not stay anymore, and hence only one element, either from the existing or the incoming set, gets chosen as the representative for all incoming elements. This motivated us to delve deeper, and looking at hindsight, one can now relate the use of the thresholded S variable in our TMCOSS formulation. Going ahead with this method, we evaluate it on driving simulator CARLA and some real-world benchmark datasets. We use the conditional affordance learning or the CAL model as the driving model on the dataset we collect using CARLA simulator. We also use DeepLab v3 Plus as the semantic segmentation model on Cityscapes and Berkeley Deepdriving dataset. Here we discuss episode completion results on the driving model only. Episode completion refers to reaching from a given source to a destination. We assess it on different tasks like driving straight or in one turn or both of them in dynamic conditions like in presence of pedestrians or other vehicles. CAL uses affordances like red light, hazard stop and many such for its driving decisions. Relative angle is an important affordance essential for determining the steer values important during turns. Hence, we introduce two variants of TMCOSS based on the pointwise criteria. TMCOSS TL, which is using total loss of all the affordances, and TMCOSS BL, which is using bucket-specific relative angle loss aided with other combined losses. We show the completed episode numbers for 100:20 and 100:7 compression ratio on the one-turn task. We have compared with other baselines too, apart from MCOSS, like having uniformly chosen subset or keeping only the pointwise metric or keeping only the pairwise metric. We observe that TMCOSS TL and TMCOSS BL perform better than the others, with TMCOSS BL being the clear winner. The remaining results can be seen in the paper. Here we show an anecdotal example for an episode where in the left plot of relative angle versus the cumulative distance, we can see that the car was moving straight till some point of 0.068 on x-axis, after which it has encountered a left turn. We can see that the red line for MCOSS starts deviating from a little before, leading to cumulative errors, thus failing to complete the episode. We can also see the absolute error on the right side plot, where we can notice the difference is higher for the red line from the time it started deviating. We also demonstrate this episode on the simulator, where we can observe that the MCOSS driven car on the right hand side will shift towards the sidewalk while turning, leading to a failed and incomplete episode, while TMCOSS BL will complete it successfully. In conclusion, we proposed a novel thresholded multi-criteria OSS, TMCOSS, which is effective on driving simulator as well as real-world data. We also propose a submodular variant of the optimization named as SubMCOSS. We show comparable accuracies of our proposed method to that of the whole set even after dropping 80% of frames. Thank you for listening.